Lastly, let's introduce the idea of floating point numbers in different bases. We've already seen floating points in our original 3-digit example. Floating point numbers in base P might look like this. There's digits, a decimal point, more digits after the decimal point, and finally a multiplication by the base raised to the exponent's power. This is what this means. d1 times p raised to the first power, d0 times p raised to the 0th power, plus, moving past the decimal point, d negative 1 times p raised to the negative 1 power, d negative 2 times p raised to the negative 2 power, and d negative 3 times p raised to the negative 3 power. But then the entire summation is multiplied by p to the e, where e is an integer. This changes the exponents by the same additive amount, effectively shifting the decimal point's location. Let's go over the rules. In each digit, there's an integer from 0 to p minus 1. Those are the d's. The value of the slots to the left of the decimal point are increasing powers of p, starting at p raised to the 0. The value of the slots to the right of the decimal point are decreasing powers of p, starting at p to the minus 1. And the exponent must be an integer, negative, 0, or positive. There's no limit on its range, at least in this part of the discussion. When we focus on the storage within computers and memory, there will be a limit. Effectively, the exponent moves the decimal point e places to the right. That's why these are called floating point numbers. Used together, the location of the decimal point up above and e are really redundant. On a computer, we'll only allow one digit to the left of the decimal point and then use e to get all of the float.